We summarized the basic equations of classical thermodynamics in the previous class. These led to the first and second laws of thermodynamics. But for our purpose, the most important are the discovery of two quantities, E as the function of volume and temperature, the internal energy, and S, the entropy, as a function of volume and temperature. These are the two main quantities that were discovered. V and T, the volume and temperature of a homogeneous mass of fluid, that is the natural variables considered in classical thermodynamics. Now, if we look at this, if we gather together the derivatives of E with respect to V and T, because those also follow from the equations of classical thermodynamics, then we can see that the E by dV, if I am going to remove the J from the picture, right, because we now take it that the heat and work are going to be measured in the same unit, so the factor J simply becomes 1, right? If that is the case, so I don't need E with the conversion factor J anymore. So I can write this as lambda B minus B, and then dE by dt is equal to Cv, and then ds by dv at t is given by lambda b by t, and then ds by dt Cv by t. We will increase lambda b, get rid of it once and for all from the picture, because we are not going to be dealing with that. So we make use of the basic result of Carnot, and which is later on generalized by Flagelon, and that is that J by T lambda b is equal to dV by dt. If I get rid of the J, then lambda b simply becomes E dV by dt. So the notation, if I write dV by dt with B fixed, then it's very clear, right, that I am writing the derivative of P with respect to temperature. The function is P expressed as the function of P and T. But however, when defining that function with the bar, I am saying the function that expresses the pressure in terms of volume and temperature is denoted by P bar, so that's different from the variable. Right? Then I don't really need to write it, I can write it like this. Right? So there should not be any confusion on account of the notation that is used. Right? So I can then write this as T dV by dt, and make it clear, right? Write it like this, and this simply becomes dV by dt at V. Now I may further combine these two equations and write this as dE by dV. This is nothing but algebraic manipulations. I can take into note the fact that dV by dt is given by ds by dV, and I can then write it as minus p, and dE dS by dt at V. Right? Now, what is the reason for doing this? We'll see shortly. Right? So now I have E and D as functions of E and S as functions of V and D. We also see the relationship between the derivatives written here. Now, I can ask whether E can actually be expressed as a function of S and V. The reason for that we will see shortly. ask the question from this, can I get to E expressed now as a function of S and B, right? So one should have a valid reason for doing it, because after all, if you compare this with this is both of them have the volume. So the only difference is the temperature here and the entropy here. Thermodynamics express a function of temperature and volume is handed over to us from classical thermodynamics, and temperature is clearly a more easily accessible quantity practically compared to the entropy, right? So we may ask, why do we want to do this? It will be making life difficult by trying to express E as a function of S and B. This is what Gibbs did. First paper on thermodynamics. Gibbs simply recast the equations of classical thermodynamics in terms of this equation, which he called a fundamental equation. It's a very important idea. So there's really a reason for why Gibbs chose to start this thermodynamics of reversible processes based on this equation as opposed to this. The reason he gives for him the fundamental equation means that given the fundamental equation, one may calculate or estimate all properties of a fluid as far as reversible processes are concerned. All properties associated with the fluid undergoing reversible processes can be calculated from this equation as opposed to this equation. So we need to explain why this is fundamental given this definition of fundamental, and why this is not a fundamental equation. Right? So clearly Gibbs found an inadequacy in this, which is why he chose to express E as a function of S and B. And before we address that, let us see if it can in fact be mathematically accomplished. What would the derivative of E with respect to S and B be? Right? So I can clearly see here, to compare these two, B is common, so I don't have to do anything to B. So now, given this, if I want to express E as a function of S and B, what do we have to do? To T. What do we have to do to T? As a function of S and B. If I am able to express T as a function of, let's say, S and B, then I can substitute into this, and then E will then become a function of S and B. Right? Now, can T be expressed as a function of S and B? That's the question we have to ask. And clearly we are given S as a function of T and B. So from this, if I can express T as a function of S and B, then it is possible to express E as a function of S and B. We can also ask then, what are the derivatives of E with respect to S and B? Right? So to understand that, first I will do a little bit of calculus on the side, which is something that you should know, right? Which you probably supposed to have known, but since the calculus that I am going to discuss is so relevant or important to this subject, this course, I want to just review that. The first is the question of invertibility of a function. I have y, which is expressed as a function of x. I am just considering a single variable for convenience first. Right? Now, when I say y is expressed as a function of x, the function, it automatically means single value. I don't have to say it. Whenever I say something is a function, it means it's a single valued function. That means for every value of x, there is one and only one value of y. That is what I mean by single valued function. Now, an important question is, can x be expressed as a function of y? You have to put a question mark because it's not guaranteed that x can be expressed as a function of y. So what are the conditions under which then we say, if it is possible, then we say the function y is equal to f of x, or the function f is invertible. That means x can also be expressed as a function of y, which means it's a single valued function of y, which means for every value of y also, there is one and only one value of x. So, what are the conditions under which this is possible?
It should not be any non-linear.
Cannot be any non-linearity, you see. What about y equal to x cubed? Is it invertible? How would y equal to x cubed look like? We talk about real valued functions. We are going to plot y equal to x cubed. How would it look like? Can you plot? Something like this. You have to be a bit. There's a point of inflection here. It is somewhat flat here. Quite flat. So is it invertible or not? So invertible from single valued function, I have to draw lines back perpendicular to x or parallel to y. If it intersects at one point, then it's a single valued function. That it is. Invertibility means I draw horizontal lines and it's also sitting at only one point. It is invertible. Is it linear or non-linear? Non-linear. So linear, non-linearity or linearity is not necessary for invertibility. It's certainly sufficient. Yes. What is the condition? 1 into 1 function, yeah. What is the proper condition? That if I plot, I can see in terms of a derivative of f. Let me give you a clue. The derivative should not be what value?
So, the domain or range should not be infinite or...
No, I'm not talking about domain or range. Confusing the matter. I put the question more specifically. What is the condition that we are considering differentiable functions? There's a differential condition for invertibility. I want that. Derivative should not be 0, right? But all of these things, so I will reframe the condition slightly. What the condition of invertibility says is only what is known as a sufficient condition. And it's also, the whole question of invertibility is local. The function may be locally invertible, but it may not be globally invertible. This function is globally invertible. The whole range of x, it's invertible. Right? Similarly, a linear function y equal to x, consider a linear function. It is also invertible, very obvious, right? However, if I were to plot y equal to x squared, it will look like this. Clearly, this function is not globally invertible. I say globally. Any domain that contains x equal to 0 will mean that the function is not invertible. Right? So you consider any domain around this, you can see that for every value of y, there are two values of x. why I mean locally is if I take this point, right, then clearly I can always consider a small domain around it. The derivative is not 0. So what it means is if the derivative is not 0, then the invertibility condition says that the function is invertible around that point in a small neighborhood. Small or large, it depends on, the theorem doesn't say how large the neighborhood could be. Clearly here, if I consider a large domain around this, the function is not invertible around that same point. It's a condition of invertibility is local and it's also sufficient. So the condition of invertibility says that if at some point x naught, that's what makes it local, f prime of x naught is not equal to 0, very important that you understand these conditions properly, right? If that means it's sufficient, if the condition is satisfied, then we can say so it's not a necessary condition. If the condition is satisfied, that means if the derivative of the function is non-zero at a point x naught, then there exists a neighborhood around x naught. Theorem doesn't help you to estimate the range of that neighborhood. It simply says there exists at least a small neighborhood in which f prime f inverse of f inverse exists. That means the function can be inverted, right? Now what about if f prime of x naught equal to 0? Then that's a point of singularity, right? So then we cannot surely say that the function cannot be inverted. The classic example is this. Here, in fact, not only the first derivative, the second derivative also vanishes for x cubed. So that condition is not satisfied, but it doesn't mean the function cannot be inverted. It can clearly be inverted even around this domain, that is globally invertible. So it's a sufficient condition. So if it is not 0, then we can be safe that there exists some neighborhood around which the function can be inverted. If it is 0, we have to be careful. It may or may not be invertible. We have to look out for possible. This is very important in numerical solution when you're finding roots, right? And this is a condition that is often minimum condition that must be satisfied. So if you have the derivative of whatever function you find, try to find the roots of it, not 0, then you can be safe that around that there is no other root, right? Something like that. But I don't want to get into that aspect. But here, if it is satisfied, let's say if it is satisfied at some point x naught, then this exists. The inverse function theorem further says that it also gives a formula for the derivative of the inverse function. In fact, says that df inverse of y by dy is equal to 1 over f prime of x. So the derivative of the inverse function is the inverse of the derivative of the original function. Common way to write this might look very confusing, right? Because I am using prime for the derivative here. The prime symbol, which means what I can write this is df by dx. The common way of writing it is dx by dy is equal to 1 over dy by dx. And from that viewpoint, it looks quite obvious. It looks like we are dividing dx by dy, and obviously it should be 1 over dy divided by dx. But we know that the derivative is not some dy divided by dx. It's just a notation, right? So there is both the convenience. It helps you remember the formula. You have to remember that this formula has no meaning unless the condition is satisfied. There is not even the function is not even defined as a single valued function. There is no question of talking about its derivative, right? So first the condition of invertibility has to be satisfied, then, right, the inverse function theorem says that the inverse function exists, and it also gives a formula for the derivative of the inverse function. Now it can be easily generalized to a function of more than, suppose now let's say, let's just make it z as a function of x and y. Now we have z expressed as a function of x and y. Right? Two variables can be generalized to any number of variables, can even be generalized to multiple functions and invertibility and all that we can talk about. But let me just introduce it for the case of two variables, z expressed as a function of x and y. Yes?
Sir, one question is that when you are writing y equal to x cube, the derivative will be 3x squared, right? For x equal to 0, then it will be 0, na?
Yeah.
So why it is inverted?
Yeah, that's what I'm saying. It's only a sufficient condition. It's not necessary. Condition f prime of x not equal to 0 is a sufficient condition for invertibility. But the condition f prime of x equal to 0 is not a necessary condition for non-invertibility. Just because this is a perfect example, just because f prime of x vanishes at some point, you cannot say for sure, right, that the function cannot be inverted. You have to understand that you have a sufficient condition for invertibility. I am not aware of any necessary condition for non-invertibility. Distinction between necessary and sufficient condition. I hope, I don't want to get too bogged down for it. These are mathematical terms, necessary and sufficient condition, but they have the same meaning as what you would use in normal usage. Necessary and sufficient, you should know what they mean. If you know or understand what they mean as per the English dictionary, you should be able to understand what I am trying to say. And I've given you also an example of what I mean by that. Right? So now if I have two choices here. I can invertibility can be with respect to both x and y separately. I can also ask, can x be expressed as a function of z and y, or I can ask, can y be expressed as a function of z and x? Both are possible. I will just take one and I will have, maybe I will just have it this way. Can x be expressed as a function of z and y? This is a generalization of the inverse function theorem to functions of more than one variable, because more possibilities are there for the inverse function. So I can ask this question, let me do it here. It is somewhat important. This is the one that we will be using here. So I can ask this question. Now, again, it's a necessary, it's a sufficient condition. So I say that if at some point x naught y naught, so it's always a local condition. At some point x naught y naught, dz by dx is not equal to 0. So if I want x to be expressed as a function of z and y, then it's a derivative of z with respect to x. If I ask the question, can y be expressed as a function of z and x, then it will be the derivative of z with respect to y that should not vanish. But I am not going to write that. If I know one variable, whenever you have a particular variable case, you can always choose the variable x in a suitable manner and then write down the formula. So that's a sufficient condition. Then the question is, what are the derivatives of the new function with respect to the variables z and y? There are now two derivatives, because here x is expressed as a function of y, there is only one derivative, dx by dy. It's related to the derivative dy by dx. Here I can ask, what are the formula for the two partial derivatives of x with respect to z and y? So I write this as dx by dz y. This will be directly analogous to the formula in the single variable, because that's the variable I will say are being interchanged right? Which is interchanging z and x. X now becomes the dependent variable and z becomes the independent variable in this new functional representation, right? So the two variables that are interchanged, the derivatives will have the same form. So this is simply 1 over dz by dx y. The other formula is somewhat difficult to remember because there is a negative sign, dx by dy at z, right? That's the other partial derivative. It will be minus, denominator is the same, dz by dx y, right? On top, I'll have simply the other derivative. It's quite easy to remember. So, important thing to remember is that why this condition in fact is needed and why these formula are meaningless without that condition. Whenever you are dividing by a quantity, you always have to watch out for that quantity, the possibility of that becoming 0. Then that derivative might not have any meaning. It's blowing up. Then we say it doesn't exist actually, mathematically. So clearly, this is the condition, right? That is why it becomes important to establish this before we divide and get the derivatives. So this is appearing in the denominator in both the derivatives. That's very important to remember. So once you remember the invertibility condition, then that derivative, which appears in the invertibility condition, right, will appear in the denominator for both the formula. Now for the variables that are being simply interchanged, straightforward generalization of the formula for single variable. The other one, the other derivative would come on top. The other derivative is dz by dy, but there is also a minus sign. It's part of the formula that you have to remember, right? So this is what we have. The other rule, this is concerning the inverse function theorem. There is also another theorem called the implicit function theorem, right? This is as much I want to say about the inverse function theorem. That the inverse function theorem can easily be derived from the more general implicit function theorem. But what the implicit function theorem says has to do with regard to implicit representation of functions, because not always it's possible to express a function in this explicit form. Often what you would have is, it is a relation, function is a relation between two variables. It might not be possible to express either y in terms of x or x in terms of y. Both might not be possible. But in which case, you can express the relation in terms of what is called as an implicit function theorem. You can also make it a constant if you want. You can always include the constant within the function. So it's a fairly general representation of an implicit function. Classic example is the circle. If you look at the circle, we have given 3 examples, but 2 of them are invertible, 1 is not, right? The circle, neither it can be expressed as y as a function of x, nor it can be expressed x as a function of y. So not a function either way. It's a very common curve, right? So it doesn't have any explicit representation, either y in terms of x or x in terms of a single value function of y, right? So then the implicit representation comes in handy. X squared plus y squared equal to some constant, right? So the implicit function theorem says, now I can ask here, is y expressible as a function of x? I can ask. That means what it means is, numerically, if I give a value of x and solve for it, can I be assured, right? I can solve for it. Might be an implicit representation, but if I want to solve y in terms of x, that means if I give a value of x, is there only one value of y, or is there multiple eigenvalues of y. That would establish whether y is a single valued function of x or not in a particular domain. Again, the conditions are local. I say that this is possible around a point x naught, y naught. This is possible. I again have to put a question mark. May or may not be possible. Right? Then, the implicit function theorem says is if df by dy at x naught, y naught not equal to 0, so whichever variable you want to express in terms of the other, the derivative of the function with respect to that variable. If I ask the question, can x be expressed as a function of y, then the condition would be df by dx not equal to 0. Df by dy not equal to 0 has to be satisfied. It's again a sufficient condition. If that condition is satisfied, implicit function theorem says there is at least a small domain, neighborhood around that point where y can be expressed as a single valued function of x. Again, it doesn't say how wide that domain would be. You have to go and find it numerically. Right? Then the question arises, what is the derivative dy by dx is? Right? It gives a formula for that also. Whenever you're dealing with either the inverse function theorem or the implicit function theorem, so many forms are available, multiple variables, multiple functions and so on. Always first question is it possible? Is something possible? Right? That's a sufficient condition normally is given. Once you've established the possibility of a particular representation from a given representation, then the question is, in that representation there are so many derivatives. What are the formula for those derivatives? That also these theorems give normally. You should be aware of that. dy by dx is simply given by minus fy by fx. By fy I mean df by dy. By fx I mean df by what's the reverse. Gives the formula. I mean, you have to be aware there are limitations with the formula. It's dy by dx, that means you expect it to be a function of x. What you're getting on the right hand side is something that's a function of both x and y. It's a limitation of the formula. So the implicit function theorem does not give you the explicit form for this, that you have to find numerically and trace out the curve, but it certainly gives the formula for the derivative of y with respect to x. This can be easily generalized to multiple variables. Suppose I have a function that is a function of n variables x1 up to xn and an n plus 1 variable y. I want to just distinguish one of the variables. So if I have one function among these n plus 1 variables, then I can certainly express one of the variables in terms of the other n variables. That much I can ask. Again, I can ask, can y again the answer is yes, the condition is the same, df by dy of fy not equal to 0 at some point which would now be x1 naught, x2 naught, xn naught, y naught. Right? And then we can ask what are the derivatives of y with respect to now each of the n variables. There are n partial derivatives now. The implicit function theorem gives formula for all of them, and it's very easy to infer from this. dy by dx1 is minus dfx1 by fy and so on. So I can write common formula dy by dxi, where I can go from 1 to n is minus df by dxi by df by dy. Again, the condition, it says something should not vanish, that derivative will always come in the denominator. I'll leave it as an exercise for you to show that this formula can actually obtain from the implicit function theorem by writing this as z minus some function of xy equal to, define this as a new function, let's say g of x, y, z. So the inverse function theorem is a special case of the implicit function theorem. Right? This is as much for these inverse and implicit function theorem. We encounter them repeatedly again and again. So you should be very much aware of these formulas. If you are not sure, or if you have followed a different notation, you can go back to the books you are comfortable with and just review all of this. Another important rule from calculus concerned with differentiation is the so-called chain rule. And again, I give a particular form of the chain rule that would be useful repeatedly. And then we'll stop, because this lecture is more about maths than thermodynamics. But you see the relevance of all of this. Now, suppose again I have, let's say, a function z of this again can be extended in various forms, right? So I'm just considering for simplicity z as a function of x and y, and then in turn I have x and y, which may be expressed as a function of certain other variables u and v, right? So because of this, now z can also be considered as a function of u and v. Because z given to me as a function of x and y, but x and y I know can be expressed in terms of u and v, which means that z also has a representation in terms of u and v. Now I can ask, how are the derivatives of z with respect to u and v related to the derivatives with respect to x and y? So a very convenient way of writing this is zu is zx times xu plus zy times yu. I'll write it out once in full detail. What I mean by that, because it's very important, because I'm using the variable z for both the functional representation, because it's very convenient to write it that way. So what I mean by this derivative is dz by du with v fixed. That means I'm referring to z expressed as a function of u and v, and I'm asking for the derivative of z with respect to u with v kept fixed. That's always the meaning with partial derivative. When you're differentiating again with only one variable. So it's much like the single variable derivative, because all the other variables are kept constant. But however, it's very important to remember which of the variables that are kept constant. So that is why you should always be explicit about what are the functional representation of a particular variable, because the confusion will arise. E can be expressed as a function of t and v. E can be expressed also as a function of s and v. So when I know that E is a function of two variables, right? And if I just write it as dE by dV and leave it like that, it doesn't have any meaning unless I say what is the other variable that is kept fixed, right? So this is the meaning of this. Now this is dz by dx, y fixed. That means I'm looking at this, the original function, plus or times dx by du with v fixed plus dz by dy, again x fixed, and dy by du. So here I am talking about these representations. So the whole notion of independent versus dependent variable is somewhat nebulous. Nothing like a fixed independent variable, a fixed dependent variable. You have to be very aware of that. So therefore here x and y are independent variables. But when you look at it here, they are dependent variables when expressed in terms of u and v. Right? So what is the status of a particular variable depends on what is the context you are considering. In the same way, I can write zv is z xp plus z yp, and you can expand it out. Right? Now there are some special forms of this chain rule that we would encounter. We've already encountered one which I didn't quite explain, and that had to do with the pressure, which is now a function of B and T from the equation of state. But given that B is a function of time and T is also a function of time, I can consider B as a function of time. Right? So always better to write it B of T. B is P bar, D of T, D of T. Then you can easily infer the formula. So there is only one variable. You can, for instance, regard, so if I call x as B and y as T, right? And then here there is only one variable, right? So B and T are both functions of, so U can be replaced by T. So we have to talk about only one variable. This is the total derivative of B with respect to time. Clearly that is given by this formula. The first one is all I need. Set x, so the first variable in the original representation, this would be dB by dV at T times dV by dV plus dV by dt at T times dt by dt. It's the time. That follows from that more general formula. There are some other functional relations. For instance, sometimes you could express y as it is and x plus x as a function of u and y. That's also possible. You may wonder how that is. We see examples. So that time actually becomes slightly more difficult to write down those formula, but they can all be inferred from the general formula. We'll see how to do that as we go along. Are there any questions? So there's some question on the books. I will certainly hand over the syllabus sheet tomorrow, where you'll find the list of textbooks for thermodynamics. What has been covered in terms of the history, there are two books that are certainly not available in our library, but they may be available as soft copies from the internet. And those are one is called as a, by Brewster, it's called as a tragicomical history of thermodynamics. Those of you, it's not really relevant for this course actually, but since some of you asked me if you're more interested in knowing about the historical developments that led to the first and second law, then these are the books, and then you also have Brewster and this Haraka, Concepts and Logic of Classical thermodynamics. Now, as far as mathematics is concerned, if you want to review this, I'll give you another reference. Kuhn and John, Calculus and Analysis, volume 2, not the entire volume, portions of that volume. It's a good reference book if you're somewhat shaky about mathematics and you expect that you would be requiring knowledge of mathematics in future as well. That's a very good book for calculus and various other things it has. A very reliable book. Right? Volume 1 is also there that deals with single variable. For our course you would need this, but I'll be summarizing whatever is required here. Maybe add volume 1 and. But for thermodynamics itself, some books, since we'll run out of time, I'll inform you tomorrow what are the books to follow from the course proper, which we haven't yet started. Right? So whatever we have covered until now, these references will be sufficient. Any questions? Okay, if not, we'll meet tomorrow.